fazer só o que eu disse que ia fazer na última aula e aí parar. Então, alguns dos teoremas que a gente já tem. Oh, shoot, right. So some of the theorems that we already have is that if this guy is a ring and this guy is a non-zero divisor, then we had an equality on that. Well, we analyzed this morphism. Oh, and this is a non-zero central divisor. Central left. So that we look at this ring and analyzing this and picking a module over this guy. When I write an S module, then we could look at that guy as an R module and look at what is the projective dimension over R of this M. And we had an inequality that compared, this was a less or equal to the projective dimension of S over R, that's 1, and the projective dimension of M over S. But in this case, these are equal. So for hypersurfaces, we proved that these were equal, assuming that it's that this is finite. So assuming that the projective dimension of M over R is finite. Okay, so the next one that we proved was, well, let's grab a module over M itself, but now let's require R to be Noetherian. So if R is Noetherian, and now we have some extra conditions. So now we'll grab M, which is a module over R now. We'll grab an X on R. And this is a non-zero divisor both on R and on M. So it's a central non-zero divisor on R. And it's also a non-zero divisor on M, meaning that if M is non-zero, then Xm is non-zero. Then in this situation, and also we'll require that M is finitely generated. Now this situation is slightly different. We are starting with a module over M, and we're pushing it forward to this, well, pushing it forward to this S, although that's called a pullback. But the point is that the projective dimension over R of M is bigger or equal than the projective dimension over R mod XR of M mod XM. So that's, this module here is obtained from the module M by tensoring over R with this ring S. Whether this module M here as an R module is obtained just by restriction of scalars. So these theorems are the two theorems that we proved so far. And both of them, well, no, this one here was essentially just an application. But this one here required that idea that you have your module, you pick a free module that surjects into M, and look at the kernel, and here you use that R is Noetherian and that M is finitely generated to get that the kernel is also finitely generated, and then use induction because the projective dimension of the kernel is less than the projective dimension of M. So that was the whole idea here, and that we repeated that idea, and we're going to repeat this idea today. All right. Okay. So the first thing I want to do is I want to analyze this theorem where we look at this ring. So instead of R, let's look at polynomials in a variable with coefficients in R. Again, R might not be commutative, but X is central in this ring. X does commute with all of R. Okay? So this situation is described here. Let's pick that R is Noetherian, so that this ring is also Noetherian. So X is a non-zero divisor, which is central in this ring, which is Noetherian. Okay? So here R is Noetherian. So that the polynomial ring is also Noetherian. Let's pick a module over R. And this gives us a module here, which is just by polynomials in M with polynomials in a variable X with coefficients in M. Okay. So this is an R of X module. And the claim is that the projective dimension of this module over this polynomial ring, this is where I left last time, is the projective dimension of this module over R. So that is if I have a module over the point and I just spread it out over the line, just taking the trivial module over the line, whose fiber is my M, then I just get something that doesn't increase the projective dimension. So let's prove this statement. Now, this theorem here applies. R is Noetherian, therefore R of, so here R is the polynomials in R. So R of X is Noetherian. Oh, no, not true, it does not apply. Let's M be finitely generated. So now that theorem applies directly. M is a finitely generated R of X module. Here is M of X is finitely generated because it's just any generators of M are going to be generators of this guy as an R of X module. X is a non-zero divisor in R of X, and it's also a non-zero divisor in M of X. So therefore, I get this inequality that says that the projective dimension over R of X of M of X is bigger or equal than the projective dimension of R of X divided by X R of X of M of X divided by X M of X. And this ring here is just R, and this module here is just M. So I get that the projective dimension of this guy is bigger or equal than the projective dimension of this guy. So the converse is that pick any projective resolution of M. Yeah, so this time I want to finish even before 2:30, or at least before 2:15. So take any projective resolution of M in the category of R modules. This is a projective resolution in R modules. Then I claim that P of X dot, so this is what? Is the complex that is given by Pk of X, so polynomials in X with coefficients in Pk mapping to Pk minus 1 of X. Polynomials with coefficients in Pk minus 1, where if you have a polynomial here of the form the sum of Pi x to the I, and here your differential was like this, then you just send it to the sum of d of Pi x to the I. And it's clear that this thing is still a differential. And each one of these guys is projective because it's a tensor product of a projective module with a free module. R of X is free as a R module. And remember that tensoring by R of X is the adjoint. So this guy is flat since it's free. So tensoring is exact And in general, it would preserve injections, but it would preserve injectives if it's adjoint to an exact guy. So, well, anyways, so this guy is free, so tensoring over R by this is exact. So that's that thing there, Pk or P dot of x gives a resolution of M of x. You just grab this complex, you tensor it with R of x, and since it's tensoring by R of x is exact, this thing is still exact, and each of the elements is a projective module. Okay, so this means that if M has a projective resolution of length n, then M of x has a projective resolution of length at most n. So the projective dimension of this guy has to be less or equal than the projective dimension of this guy. Because for each projective resolution of as R modules, I constructed one of the same length as R of x modules. So that means that we have also this inequality. And therefore, these two are equal. I'll throw it here. All right. Okay, so if I have a module over the point and I spread it over the line, I don't increase the projective dimension. But the theorem that I started to prove was the following theorem. And essentially, I think hopefully here's where I'm going to stop. Is that if you look at polynomial rings in n variables, here, and you look at the global dimension of this guy, then this is equal to n plus the global dimension of the polynomial of the ring R. So that's what I wanted to prove. Okay. So the first observation we made is that we can prove by induction on the number of variables. Induction on the number of variables on n reduces to proving that the global dimension of R of x is equal to 1 plus the global dimension of R. So if I prove that, then you just apply that theorem n times and you're going to get this. Okay, we see that 1 plus the global dimension of something here. So let's apply that, this theorem. Let's apply this theorem that we have in that situation. But this theorem here doesn't have any conditions except that x should be a non-zero divisor on this ring R. So I'm going to take R to be R of x. X is that x, and it's a non-zero divisor in R of x. And we see that since, so in that theorem there, this module M is a module over R mod xr. So now for every M which is an R module, what we see is that the projective dimension over R of x of M, that's what that theorem is saying. I'm taking R in that theorem as R of x, is 1 plus the projective dimension over the ring R, which is equal to the ring R of x divided by x R of x of my module M. And this is over all R modules. So if I take the supremum over all R modules, the supremum over M in R modules, well, this thing here, by definition, is going to be the global dimension of the ring R. And here I'm going to be taking a supremum over R of X modules, but only R of X modules that are of the form pullbacks or restriction of scalars of R modules. So whatever I get here is going to be something that it's strict, well, not strictly, but it's less or equal than the global dimension of this guy. Okay? So what I'm seeing is that the global dimension of R of X is bigger or equal than this. Okay? Oops, sorry. Okay? Because I may have some R of X modules that admit projective resolutions that are of length more than what I need here, than those modules have. Okay. So now I want to prove the converse. I want to prove that the global dimension of this guy is less or equal than this. Okay. So to prove that the global dimension is less or equal than something, I need to produce explicitly for every module. I need to produce for any R of X module. I need to produce an explicit resolution of the corresponding length. Yeah, so I think I'll start here. I probably want to keep this too. So let's take M to be an R of X module now. So let's take M to be an R of X module. Now, again here, even to apply that theorem, I needed the projective dimension of this M to be finite. So notice that if the global dimension of this ring is infinite, then this guy is also infinite. So I can reduce to the case where these two numbers are finite. So I can just take an R of X module which has finite projective dimension. Let's suppose that it has finite projective dimension over R of X of M, which is just N, just some number. Okay, so the trick is to do the following, is to look at the following sequence. Let me write it first and then we'll see what it is. So M is an R of X module. But then if it's an R of X module, it is an R module. And here I am viewing R inside of R of X. And I'm doing restriction of scalars. Okay? So the restriction of scalar is just M where I forget how X acts by multiplication. So that's an R module. This is different than modding out by X, which is what we have been doing in all of these applications. Okay? So I started with a module here, and I'm not looking at M modulo X acting on M. I'm looking at M where I forgot how X acts. So that's this M, which is an R module. Now, R of X is an R module, again, because of the same embedding here. So that's the tensor product of two R modules. And you have to be careful if your ring is non-commutative, whether you're looking at one is on the left and the other one is on the right. And I'm not going to be worrying about these things. The same thing here, so that's the same object. And I need to tell you what this map is and what these maps are. So M here is an R of x module. That's how I started with. So if you give me some polynomial p with coefficients in R and some element in my M, then you map this to P acting on M. So this is the action of this ring on M. M was a module over that ring. Notice that this action is this map is well defined in the tensor product over R. Namely, if you multiply your polynomial by an element in the ring R, it's the same thing as multiplying by M. This is in this tensor product by that element R, and it doesn't matter where you act because this is what's well defined. The action was given in such a way that this is equal to PRN. Okay. So again, you need to be worried about whether your module was left or right. I'm writing this as if my M was left module. Okay. So this was just to say that the action was well defined in the tensor product. So this goes to P acting on M. So that's that map. The map here, on the other hand, is slightly different. If you have a polynomial here and an element in M, what you can do is two things. You can multiply your polynomial by x and leave your element alone, or you can multiply your element by x, because M, here I'm using the action of R of x on M, even though I had forgotten it when I view it as an R module. So I could do this, and you can take the difference. Again, this is well defined over R. So if I multiply by an element by R, P, I multiply it by R. That's P times R here, but X is central. So that's the same thing as P X R, and then I can just move that R on this side. And the same thing here, P times R, I can just move it on the other side. And again, X, since X is central, I just move it also on the side of M. So P times R tensor M maps to the same thing as P tensor R times M. So this is well defined on this tensor product. Okay, so that gives me a sequence, and I claim this sequence is exact. Okay. The fact that this is surjective is obvious. So the last surjection is obvious because one tensor M maps to M. The injection, so this is surjective. This is injective, and this is also obvious because any element here, right? Any element of R of X tensor over R with M can be written as a linear combination like this, like a sum of X to the I tensor Mi. I goes from 0 up to some number, and I've already chosen K, where Mi is in M. And I'm absorbing all of the coefficients that in principle are in R. I'm just passing them to Mi because I can multiply by R on Mi, and this tensor product is over R. So I can just write any guy here, I can write it in this way. And once you write it in this way, and you map this, so the leading monomial, let's suppose that this Mi, the last one is non-zero. So let's require that Mk is non-zero. So that's the leading term. The degree of this guy is K, and Mk is the last coefficient in M that I have. So that's the highest degree. Then the degree of this map, right? So if I apply this map, we call this I, to this guy, I on this sum, oh shoot, Yeah, I is a bad name. This is going to be iota. So iota on this guy, well, I need to multiply the first guy by x, so I'm gonna get a sum of x to the I plus 1, tensor mi, and I goes from 1 to k, minus the sum of x to the I tensor x times mi. And I goes from 1 up to k. And you see that the leading monomial of this thing is x to the k plus 1 tensor mk. The leading monomial is of this expression of star star is x to the k plus 1 tensor mk. So now if iota, and this is the only monomial of that degree, so if iota of this term here is 0, this implies that mk is 0, and this is absurd. We assume that mk was non-zero. So iota is injective. So this map here is injective. And now we need to check that the kernel of pi is the image of iota, which is exactness at this point in the middle. So let's take something in the kernel of pi. So let's suppose that we have some polynomial, xi tensor mi from 1 to k. And again, let's assume that mk is non-zero, which is in the kernel of pi. Let's suppose that pi on this guy is equal to 0. Well, no, I should have checked something before. I need to check that pi of iota is 0. But that's obvious. So if you apply pi to this element, what you get is p times x acting on m minus p acting on x on m. And m was an R of x module, so this associativity is the definition that m was an m module. So this is 0. So we know that the composition of these two things is 0. And now I'm only left to proving that the kernel of this map is the image of this map. Okay, so let's suppose that we have an element in the kernel, which is this guy. And I'll do induction in the degree. Let's prove by induction. By induction on K that the kernel of pi is equal to the image of iota. So if K is equal to 0, oh shoot, I is equal to 0 was fine here. Here is not. Here is not. I can have constant terms. So if K is equal to 0, then what I have is just one tensor m0, and pi of this is equal to 0. But this is the same thing as m0, which is equal to 0, which, well, that doesn't happen. So for degree 0, we have that the kernel of pi is the image of iota. So let's assume that we know it for up to k minus 1, and let's prove it for k. So let's take something in the kernel like this. Okay. So what we can do is the following. We can grab this guy here, and let's look at, but now I'm assuming that k is bigger than 0. So suppose that k is bigger than 0. In particular, k minus 1 is less or equal, is bigger or equal than 0. Okay, so what I can look at is at the sum of x. Well, I don't even need to take. I can do this. I can look at x to the I minus 1. K minus 1 tensor mk. This is not going to fit here. Let's do it here. Let's grab x to the k minus 1 tensor mk, and let's apply iota of this. So this is some x to the k tensor mk minus x k minus 1 tensor mk. Oops, tensor x times mk. Okay. So now let's grab our element, which was this full polynomial, xi tensor k from I is equal to 0 up to k. And let's subtract iota of this guy. And let's apply pi. Now pi of this is 0, and pi of this is 0 because it's pi of iota of something. So this is in the kernel. But on the other hand, this thing here is the leading monomial of this is that, which is equal to the leading monomial of this polynomial. So this thing here has degree k minus 1, or less or equal than k minus 1. Because the only thing of degree k which is tilted. Okay? So since this guy has degree less or equal than k minus 1, this thing here has to be in the image of iota. So this is in the image of some x to the I tensor m bar I. That's by induction. Okay, so this is something in the kernel of pi, therefore it is in the image of iota. Okay, but then now we're seeing that this implies that the sum of x to the I times mk from I is equal to 1 up to k is equal to this term, this iota of the sum of x to the I tensor n bar I, and this is of degree less or equal than k minus 1. So this is plus this x k minus 1 tensor mk, which is in the image of iota, which is what we wanted to prove. Okay, so that sequence there is exact. This sequence here is exact. Oh no, I didn't want to remove this. I think I'll need this theorem again. So, okay. So I claim that this sequence is exact. Let's remove this. Okay. So once that we have that sequence, let's run the same ideas in proving those theorems. This M was an R of X module, and I have this short exact sequence. This says that the projective dimension of this guy is one more than the projective dimension of this guy. So the projective dimension of M and remember what we got is that the projective dimension over R of X of M, so in this theorem, the we're looking at this M as an R of X module. And we took the supremum over all these R modules. And we got that the global dimension plus 1. And here we got something that was, that the global dimension is bigger or equal than something. So now I'm trying to look at, trying to bound the projective dimension of M as an R of X module. I want to prove that it's less or equal than something. But this sequence here is telling me precisely that the projective dimension of this M is less or equal than 1 plus the projective dimension of that guy, of R of X tensor M over R. Okay. Same argument as always. You look in the category of R of X modules, and you look at X from this guy into anything, and you look at the long exact sequence, and that's X for this guy is the same thing as X for this guy shifted by 1 degree. So if this guy has projected dimension n, it means that after n, that those X groups are 0, and this means that after n plus 1, the X groups of these guys are going to be 0. Therefore, the projected dimension of this guy is less or equal than n plus 1. So that's this condition that we keep applying all the time. Okay, but now we just got that this is the same thing as 1 plus the projected dimension. Now it's the theorem that we just got. This thing here as an R is polynomials in M with coefficients in X as an R of X module. And we just checked that this is the same thing as the projected dimension over R of this M. I should do this. Here I should just kill this X. So that's the theorem that we just proved. And well, that's it. So that's, now we look at the global dimensions on this other side, and we get the inequality on the other side. So here we get, so we obtain that the global dimension of this R of X is less or equal than 1 plus the global dimension of R, which gives us what we want. Okay. Corollary of this is the theorem that we wanted, is that if K is a field, the global dimension of K of x1 up to xn is equal to n. This is just simply because the global dimension of the field is 0. And in particular, this means that this implies Hilbert's questions. This answers Hilbert's question. Because if you give me M, any module over any finitely generated module over this ring, then the projective dimension of that module is less or equal than n. Because the global dimension of this ring is n, then the projective dimension of M is less or equal than n. This means that for any resolution of length less or equal than n, so that means if you have an exact sequence like this, PD into PD minus 1 into P0 into n, 0, which is exact, and the PIs are projectives, this implies that n is projective. But a projective, well, yeah, it's just that. Remember, this was the question that Hilbert essentially asked. Okay. Let's continue with that section and let's finish what I started last time, which was studying modules over local rings and how their fibers were at the special point. So here, R didn't need to be commutative anywhere, but now it is. Now I'm going to be looking at R is going to be local rings. So R is going to be a local ring with M in R, its maximal ideal. Okay, what did I prove last time? I proved that if you have P R module, which is projective and finitely generated, projective and finitely generated, then it was free. Okay. So that's something we proved last time. So now we're going to prove a strengthening of this theorem here. Instead of so I'm going to prove a strengthening of this theorem where instead of having an inequality, we're going to have an equality. And then we'll stop right there. So for local rings, understanding the reduction modulo, an element that vanishes at the close point. So an element in the ideal, in the maximal ideal, which is a non-zero divisor, this thing satisfies an equality. So the theorem is this. Theorem, let R be a local ring and X inside of the maximal ideal of R a non-zero divisor. Let M be an R module such that X is a non-zero divisor. Which is finitely generated. Then the projective dimension over R of M is equal to the projective dimension over R modulo XR of M modulo X. Notice, so remark, R mod XR is also local, is still local. Oops. Okay, so all right. So what's the picture here? So the picture is you have some space, you have some subvariety, and you have a point inside of that subvariety, and you look at an infinitesimal neighborhood of that point inside of the ambient space. So this local ring of functions here is this R, and the intersection is an infinitesimal neighborhood of the point inside of the subvariety, this is this ring R mod XR. And what we're taking is a module on the whole ambient space, but just on this infinitesimal neighborhood, and restricting it to the subvariety, and we're saying that this projective dimension didn't change. So if you needed n bundles to resolve on the ambient space, you're still going to need n bundles to resolve on the subvariety, and no less, which this would imply. Okay, so let's prove that. And let's prove this by induction on the projected dimension of that module. Again, it only matters when this thing only matters when M has finite projective dimension. So let's assume that the projective dimension of M, so we're going to do induction on this projective dimension of M over R. Let's call it N, and let's do induction on it. Okay, so if n is equal to 0, this implies that M is projective. But M is a projective finitely generated R module, and R is local. Therefore, M is free. But if you have a free module, then this reduction is also free. And if it's free, then it's projected. Now it's an R mod, XR module. And therefore the projective dimension is 0. So 0 is equal to 0, and we're in good shape. Well, probably I didn't need to do anything about this, because we have this inequality anyways. Sorry? It's a local ring, so it has to be, yeah, it's a Noetherian local ring. So if you have a, yeah. Okay. Yeah, so this was a silly computation, but anyway, we just checked that 0 is equal to 0. Let's do this. Let's do this induction on the projective dimension of these guys. So, and we'll do the same thing as always. We'll just cover it by a free module. How does it go? We'll just cover everything by a free module, look at the kernel, and play the game that the kernel has projected dimension 1 less, and try to do that. That's how we can do this induction on this on the projected dimension. All right. So the first thing I want to prove is the following. want to understand this condition of when the restriction is free. Let's see if this is right. So let's suppose that M is an R module, finally generated. And let's suppose that this M is free. So this is a statement that I have something on the ambient space, I restrict it here, and it became a free guy. It's just a bundle, and it's a trivial bundle. So what I'm trying to check is that I never have a strict inequality here. So I'm trying to check that, if this guy was free, then I needed 0 bundles to resolve it. Therefore, I should need 0 bundles to resolve it here. Therefore, if this guy is 0, I want this guy to also be 0, meaning that M should be projective. But if it's projective over a local ring, then it has to be free. Yeah, so probably I should have done induction not on that projective dimension, but on this projective dimension. And then this 0 is equal to 0 is something that we need to check. So let's look at this guy being free. Then we know what we want. If the theorem is true, then this would imply that the projective dimension of M is 0. Right? Because the projective dimension of this guy is 0. But if the projective dimension of M is 0 is projective, finitely generated over a local ring, therefore this guy is free. So this is something we need to check. So let's prove that. And I'm going to be doing induction not on that end. I'm going to be doing induction over this end. Okay. And yeah, and that makes more sense. Sorry about that induction on end there, because since I have this inequality, then I can actually restrict to the projective dimension of this guy being finite, because if this guy is infinite, then this guy is also infinite, and they are equal. So let's restrict to the projective dimension of this guy being finite, and let's do induction over that end. So let's forget about this, which was just a stupid check of 0 is equal to 0. Let's do induction on the projective dimension over R mod XR of this M mod XN. So let's suppose that this guy is N. And let's do induction now. Let's suppose N is equal to 0. Then if N is equal to 0, it means that this guy here is projective over a local ring, therefore it's free. And I want to check that M is free. That would be something that we need. Checking this is the case N is equal to 0. So this is the case N equals 0 in our induction. So let's prove this statement. And this is a non-trivial statement. So let's take a basis, M1 bar, MK bar, K bar. This is a basis of MXN. So we lift them to M. To M1 up to MK in M. And let's look at the submodule generated by these guys inside of M. Okay. So let's call this submodule N. So if N is a submodule of M, which contains all these elements M1 up to Mk. So what do we know about this M? if I mod out by x, then these guys generate the whole of m modulo m xm. So m is equal to that n there plus xm. But then, in particular, this is equal to n plus the whole maximal ideal, m. This is because x is in the maximal ideal. So this is strictly larger than this. Well, this is larger than this. But since m is finitely generated module over a local ring, this condition here was Nakayama's lemma, telling us that n is equal to m by Nakayama's lemma. So this means that if you just lift a bunch of generators of this guy to m, these guys are generators of m. Okay. So the m's generate m. I think now I can just remove everything here. I'm not exactly sure. Okay, I think I'm going to feel very stupid in a second that I kept this word for the whole lecture and I'm going to remove it right before I need it. But anyways, I'm not sure if I'll need this or not. Anyways, so now I need to check that these guys, that these MIs are linearly independent. So claim the MIs are a basis of M. So let's take a linear combination of those guys, where these Ri's are elements in the ring. And let's suppose that this is 0. Okay? So now, modulo x so if I reduce this thing modulo x, these MIs are actually, that thing looks like m bar I times Ri is equal to 0. And these guys are linearly independent in mxm. Right? These guys were a basis by definition of this guy, of this module. So this means that these Ri are all inside of the ideal generated by x for every I. Because all of these Ri's are 0 modulo x. Okay? But x was a non-zero divisor. On M and R. So I can divide these Ri's by x. Makes sense. Well, this is just a statement that Ri is in this ideal, so this makes sense. But then also this equation here means that I have these new guys, Ri, let's call these guys Ri1, Mi still is equal to 0. And just repeat this procedure. So you get a sequence of ideals. So you have the ideal generated by all these Ri's, which is included in this guy. But then you also have this ideal generated by the Ri's once, which is larger. And this guy is included in this Ri2, which is larger. And these are all ideals inside of R. And you know that these are strictly larger because each one of these generators is the division by x of the generators in the previous one. Okay? Okay, so now we have an increasing sequence. And R is Noetherian. So this is absurd unless all of these arrays are 0. So if one of these arrays was non-zero, then we get some non-trivial equation like this. We can divide that guy by x, and I can continue dividing by x infinitely. And I will get an increasing sequence of elements, each one providing me a larger ideal inside of R. So I needed all of these arrays to be 0. So that proves that the case n is equal to 0 in this induction. So if you have a module such that when you restrict to the subright is free, then your module originally was free. It's a cool statement. So you can check that a module is free on the ambient space by just restricting to subwriting, at least locally, infinitesimally locally near a point. Okay, so now we do the trick. So now we prove the case n is equal to 0. Pick. So do the same trick as always. We pick a free module that maps to m and look at the kernel. And the projective dimension of m is less or equal than 1 plus the projective dimension of k. And actually, the projective dimension of k is actually 1 less. The projective dimension, well, let's look at this modulo x. Okay. So if I look at this modulo x, the sequence looks like follows. I'm going to get m mod xm. So I'm tensoring by the ring r divided by x by xr. So this is f divided by xf, which is still free. This goes to k divided by xk. And this goes to tor1 of m r xr. And this comes from 0 because tor1 of this guy is 0 because this guy is free. So now again, this was the set of elements m in m such that xm is equal to 0. And we are assuming that this tor1 is 0. So this sequence is exact. And if this sequence is exact, the projective dimension of over this guy, r mod x r of k xk is 1 less than the projective dimension of this guy unless this guy is projected. So let's suppose that the projective dimension of this guy is n, which is bigger than 0. So then the projective dimension of this guy is n minus 1, which is bigger or equal than 0. So the projective dimension of this is the guy that we're trying to do induction on, is n. Therefore, the projective dimension of this is 1 less. So now this n, I'm assuming it's bigger than 0. Okay, but now by induction, this is equal to the projective dimension over r of k, which is therefore equal to n minus 1. And if the projective dimension over r of k is n minus 1, the projective dimension of m is less or equal than 1 plus n minus 1, which is equal to n. So the projective dimension over r, and this is also over everything over r, is less or equal than n, and we know on the other hand that it has to be bigger or equal than n. So that's it. This implies that the projective dimension over r of m is equal to the projective dimension over r mod xr of m mod xm. We already had the bigger or equal in that direction, and now we're proving the less or equal. Okay, so that finishes the proof of that theorem. And yeah, this time I'm giving you 25 minutes back. Unless there's a question, let's stop right here. Okay, so that gives back like 3 or 4 times that I